Okay, thank you very much. Thank you for coming here. So I'm going to talk about JN-SAF, which is a framework for doing static analysis for Android applications that contain native components or native code in it. This is joint work between University of South Florida, which I'm from, and the University of Electronic Science and Technology of China. The lead author of the paper is Fengguo Wei. He recently graduated, joined Google, and unfortunately, because of some immigration paperwork issues, he couldn't come here to give this presentation, so I'm doing the best that I can for this work. So we all know that in Android applications, one can have native code. So the way it normally works is you can write the Android app in Java. This is the most common way. And the Java program gets compiled into Dalvik bytecode, which will be run by the Android runtime system. And then you could also write some part of the program in C or C++ that will be compiled down to the native platform, being ARM, x86, or MIPS, and that becomes the native part of the application. And then the Java part and the native part can invoke functions from one another, and this is done through the Java native interface. So why do people want to use native code in the first place for Android applications? Mostly it's for performance reasons. Like if you have a game app, native code normally runs much faster, and it's easier to manipulate hardware resources, and that's generally more preferred for those kind of high performance applications. And the other reason is you may have already existing libraries that are already in the native code, as opposed to rewriting them in Java. You can just use that native code library in the Android application. So how prevalent are native code use in Android applications? So we did some very basic statistics from two types of data sets. One is the 100,000 Google Play apps that we got from Andrew Zhu, which is a project that crawled a large number of Google Play apps. So these apps are predominantly benign apps, because we all know Google Play has a very low rate of malware. They have done a reasonably good job in vetting the apps to make sure malware apps don't get into the Google Play. So out of those 100,000 apps, we found roughly 40% of those apps will use native code. About 60% is purely written in Java. So we only see Dalvik bytecode, nothing native in the package, in the APK. And now we also turn to another data set, the Android malware data set, which is actually from my group as well. It has 24,000 Android malware samples. These are all malware from various sources. And out of those 24,000 malware apps, roughly 22% use native code. And then the rest only use Java, Dalvik. So I use Dalvik and Java interchangeably for this talk, because presumably those Dalvik bytecode is produced from Java source code. So from this we know there's really not a big differentiator in between benign apps or malware apps in terms of whether having native code is a good indicator this app may be malicious or not. And obviously we cannot just rule out or ban native code in Java, because many apps do need to use those native portion of the code. So now why we want to analyze Android apps with native code? Well, this is mostly for security analysis. One of the reasons is malware writers also may want to use native code to achieve certain nefarious objectives. So for example, if one of the big concerns in the malware research community for Android is the app may actually intentionally leak sensitive information, and that can be done through a concerted effort in between the Java part of the code and the native code. As you can have the data being passed in between the two worlds, and the data gets leaked. So if we are not able to analyze the native part of the app, then we'll not be able to capture those data leaks. And the other way that the malware writers can use native code is to hide certain malicious behavior. So for example, if the app executes certain system commands, if you put those execution code in the native part of the app, it may be harder for certain antivirus products or analyzers to find them out. Or if the app is communicating with certain command and control server that's part of botnet, and you can put those communication functionality into the native part of the app. That can potentially make it harder to detect by either the Google Play, the vetting mechanism, or antivirus software. And the other example is there are certain ways the antivirus products detect malware by checking for certain signatures. For example, malicious URLs, premium numbers that may be dialing to give you, charge you, and malicious messages that are being sent. And if the antivirus products only search for those simple patterns in the Java part of the world, but you do this in the native part of the world, then it can bypass those detection. And these are just simple cases. I through the Huawei conversation just now, I also learned that people have found certain malware apps will use the native code to perform obfuscation. For example, it can override, modify the relocation table for Android system functions. So when you call a function seemingly benign, it's actually a sensitive function. So these things will need to be done in native code, because native code has the ability to manipulate those data structures. And if you cannot understand what's going on in the native part of the app, we'll not be able to capture those behaviors. Right. So let me give you a motivating example on how this can be really complicated. Right. So that's sort of like a contrived example, but it shows you what could happen when someone intentionally used the native code part to hide certain activity. And this is mostly focused on the first problem, the data flow, which can serve as the foundation for all the other misuse of this capability. So here, I'm not sure you can see it, but then I'm just going to highlight the most important part. Here is the Java part of the app, and here is the native part of the app is compiled from C++. And there's a source. The source means you may have some potentially security sensitive information being obtained at this point in the program on the Java world, and there is a sink here, and that's the leak when that information gets leaked to the outside world. Now this leak is accomplished through a number of rounds of data being passed between the Java part and the native part. Right? I'm not going to go through the detail, but what happens is, if you look at here, the sources in this case is IMEI, is a ID for the device, and that information first gets used to call the function toNative right here, and then that function will call another function called propagate data, and that is actually defined in the native part of the app, so that data gets passed here. And after some manipulation, now this data can pass back to another function defined in the Java world, and then another function called to go to the native part, and then that data gets leaked. Right? So obviously it doesn't make sense to do this, but if a malware writer wants to hide their actions, something like this could happen in malware. Right? So I hope I have convinced you that understanding or being able to analyze native code behavior is important for analyzing Android app security. But here's a big challenge. Right? This kind of problem involves analyzing code written in two totally different languages. The interlanguage analysis is non-trivial to be performed for a number of reasons. First of all, those two parts can call each other back and forth, and this can happen as many times as the code developer wants. But analyzing Dalvik and the native code requires totally different methods as far as we understand now. And they also require different intermediary data representation for the analysis. And then it is not clear whether it's even possible to create a unified method for both. Right? But the good news is we do have very mature systems in place for either one of them. So we have a lot of very good work on analyzing Dalvik, and we have a lot of very good work for analyzing native code. But how to combine those two types of analysis in a uniform way, and also to do the analysis in an efficient manner, that is totally not clear. Normally, when you perform data flow analysis or symbolic execution, you are sort of simulating the program's execution behavior as if the program is executing in your analyzer. But when you have to cross the boundary between the Java and native, every time you cross the boundary, you have to convert the intermediate data representation to another analyzer, and it can keep going. If you do it this many times, that'll be very highly costly, and it's not even clear that's even doable because those are two totally different analyses. So we have identified one way to solve this problem. Actually, there has been existing work in the programming language community for this type of thing. Back in 2011, Ishio Dilick at Stanford at the time proposed a summary-based bottom-up data flow analysis. So here's the sort of the nutshell on what's going on. So normally when you perform data flow analysis, you flow the facts in the program code forward. Right? So as the program gets executed, when you have a core graph here, you flow the data flow facts along the core graph, and then you keep doing this until you reach a fixed point, at which point you have derived all the possible data flow facts of this application. Right? And then we said, no, this is fine, but it will be highly cost prohibitive for our interlanguage analysis. What Dilick has shown is you don't really have to do it in this way. Rather, you can actually do it in a backward manner. And also, the very nice feature about this approach is you can also analyze each function independently and compute a summary of data flow modification for each function. When one function calls another function, like here, function B calls function C, all it needs is to know the data flow summary for function C. It doesn't need to go into function C to further the analysis. It can take the summary and use to compute the summary for function B. So as you can see, if we perform the summary analysis backward, we start from the leaf and all the way back to the root, then we will be able to compute all the functions summary as if they were all done independently. Right? Now there's one caveat here. What if there's a loop in the core graph? Now when that happens, you have to break the loop arbitrarily in the post-order traversal. When you do that, then there will be a case where when one function caller is going to call another function, but then you haven't computed that function's summary yet. Then you take a conservative approximation. That means anything could happen. So we don't know. That's still sound, but you may lose some precision by doing that. But if there's no loop in the core graph, then that's as precise as you can get in terms of context and flow sensitive data flow analysis. So we feel this will be a very good approach to address our challenge. First of all, this work has nothing to do with interlanguage analysis, but the challenge we face in the Java native code analysis is actually can benefit from such an approach, because now we don't have to worry about whether we have to cross the boundary, because every function has to be written either in Java or native. So we can apply whatever method we like for each function independently in the right order, so that we'll have the summary available when the caller needs it. So for example, if one of those, if B and D are written in native and then the rest are written in Java, it doesn't really matter. We apply a native analyzer on B and D, and then we apply a Java analyzer on the rest. All that needs to happen is to propagate the summary file from the callee to the caller. So the summary becomes the contract between the two types of analysis. You can conduct each one of them independently. Don't have to worry about context switch. So here's a quick example, this is a simplified example of what we have seen in the previous example. So you have a core graph of this potentially problematic app. You have a source here, and then there's a sink there. Based on this core graph, we compute the post order. So we need to first compute the summary of the function n2, right? And then because function n2 will call the sync method, so you are sending out some potentially sensitive information. We just say the argument of function n2 is flowing to sync at line number 15. So this is the summary. This is the summary of that function. And then we just keep doing that. And then when the caller function calls this function, it uses that summary and then keep going. And then we're going to be able to build up the data flow facts in the end, showing that in the end, the source at J17 is actually going to flow at the same as C15. So I was going pretty fast here, but details are in the paper. Basically, every step we just apply the summary of the callee. When you need to go into a function, you just take the summary and then use the summary to finish this function's analysis. And this will allow us to use different analyzer for different functions, depending on whether they are in the Java world or the native world. So that's sort of the core challenge we'll address in this work. And there are also quite a few other major challenges that we have to deal with. One is how you can resolve the native method calls statically. And then we are using an off-the-shelf existing binary analyzer, Anger, but Anger is not really designed to perform Android code analysis. So we have to do a lot of work to use the symbolic execution engine provided by Anger to do this kind of data flow analysis and the summary calculation. And that's a lot of non-trivial work and then efforts there. And we have to be creative in a lot of times. And then also Android also allows one to write a whole activity natively. So you don't even have to have any double bytecode for an activity. So you can just use native development kit to write everything for activity purely in C or C++ and compile it to native code. And that's a lot of challenges have to go into there. So the details are in the paper. The result is a framework we call JN-SAF, standing for Java Native Static Analysis Framework, is composed of two parts. One is called Java Droid, and the other is Native Droid. So these two parts of the analyzer will deal with the different types of code that we have to analyze. The Java Droid is built on top of Almond Droid, which is also from my group. And Native Droid leverages Anger, which I just mentioned, and then we heavily use Anger, and then we have to put in a lot of effort to make it able to reason about both Android and also JNI and NDK semantics, and then we run app through, and then finally we get the report of the type of thing that we have shown you in that simple example. So let me briefly talk about what we have evaluated this framework against. So the first thing we did is, because we are now introducing a new capability for an Android app analyzer, we want to create a benchmark test for those capabilities. And that has been a common practice in the past few years for the major Android static analyzer, starting from Flow Droid, followed by Almond Droid, and SCCTA, Droid Safe. So we all want to create benchmark for the new features or new capabilities that we added. So because now we are adding a new capability, we added 22 benchmark apps. These are not real-world apps. These are handcrafted, intended to test an analyzer's ability to handle that type of problem. Right? And every time the analyzer is able to find a problem correctly, you'll find a circle here. Across means this is a false negative, which means there is a problem, but then the analyzer failed to identify that. And then a star is a false positive, there's no problem, but analyzer mistakenly think that there's a problem. So the result is not really surprising because none of the other three tools, Almond Droid, Flow Droid, SCCTA, or Droid Safe, is designed to handle native code. But we just wanted to see, maybe by surprise, they could, right? But not surprising, none of those tools can handle native code. JN-SAF is able to identify most of the problem. There's a couple of false positive, and then we compute precision and record those kind of metrics. And we also tested it on real-world apps. These are handcrafted apps just to test this functionality if it can happen. We also wanted to see when we apply it on the real-world apps, what will happen? Here are some statistics, like I mentioned, what's the percentage of the apps that have native code, and then how many apps has native activity, total native methods, those kind of things. And also for the native code, we also have breakdown on the architecture. So that includes ARM 64 bits, x86, x86 64 bits, and MIPS. And these are what Angular can support. So for all those real-world apps, we also take a sample of those that consists of 10,000 components. A component is an activity, service, container, those kind of things. And then we want to see how long it takes for JN-SAF to compute the result. Here's the scatter graph. Both the x and y axis are in logarithm scale. The x-axis is the size of the methods, the number of analyzed methods in the component, and then the y-axis is the time it took to run the analysis. As you can see, it's sort of on the the running time grows on the square of the size of them on the number of methods, which is not bad. Yeah. And then the average analysis time for each component is about 42 seconds, which is also quite affordable. And we run this analyzer on all the apps in the AMD dataset, and we found these problems, and these correspond to the 4 potential misuse of native code in the app that I mentioned earlier. And here's the takeaway. So this is the first JNI NDK aware Android static analysis framework. We do plan to open source the system, so you can probably find it on this website around the end of this month. So thank you very much.
So we have a little bit time for questions. Please, Stephen.
Hello, Johannes Kinder, Roll Holloway. So my question is, where does the imprecision creep in? Because you didn't get 100% everywhere, right? So is the problem the binary code analysis, or what's the source of imprecision in the experiments?
Well, this I'll have to ask Feng Guo. Unfortunately, I did not do this experiment, but I can check with him and then get back to you. So I don't know what's the source of the false positive here. It could be due to because when we have to use Angular to perform symbolic execution, as you know, symbolic execution, you have to make a trade-off. You cannot unroll the loop infinitely. So that could be a source of imprecision, or it could come from when we break the loop in the call graph arbitrarily. That may introduce imprecision, but I don't know off the top of my head what these specific false positives are caused.
Hi, thank you for this cool work. It's Oliver Schranz from CISPA, Germany. My question is, in your examples, you showed that you mostly found those direct flows in the native code. So would it also be possible to find more indirect flows, like sensitive data being written to a file and later picked on from a Java side?
So those kind of flows, what you can do is you can, for example, you can define any write to file as a sink. Mm-hmm. And then any read from a file as a source, and then you can combine those two. So it cannot be, it's not done directly by a single flow analysis, but you could leverage this to find out more complicated behaviors like those.
Okay, thank you.
You're welcome.
Zafir from UC Irvine. Very interesting work. So have you considered collusion attack? There might be more than one app, and one app only have maybe Java code, and another app have like all the native code.
Yeah, that's a very good question. So it's actually, this is orthogonal to whether it's native or Java. You could even, for pure Java code, you could also have collusion as well. And multiple apps, they can, so because this whole thing is built on top of Android, and Android does support analyzing multi-app collusion, so that's taken care of there.
Thank you.
You're welcome.
Okay, let's thank Simon again.